spend a few hours on this site and just, commit to memory, just, really cram that information in there, walk into the test the next day and just pass it. I would actually recommend, though, that you take the time to understand. If you come across a question that you don't understand the answers to, look it up on Wikipedia. Find out what's going on there. You'll learn a lot out of it. So generally, amateur radio operators have a 1,500 watt hard limit on power. In this particular band, though, we're limited to 50 watts if we're within 241 kilometers of White Sands missile testing range. I have no idea what they're doing with the ISM band at White Sands, but they don't want ham radio operators screwing it up. In terms of what kinds of modulation you're allowed to transmit, well, this is a digital system. It's sending bits back and forth. And in ham radio terms, it's technically, there's a list of allowed transmission types and a list of allowed digital codes. But in general, you're allowed to transmit any unspecified digital code that's not explicitly called out in the list of permitted schemes, as long as the specification is published. So in this case, the EPC Generation 2 standard is published, so we're perfectly fine using it on a ham radio band. The only problem with it is that we're not allowed crypto. Well, the tags don't actually support any crypto. You're not allowed to obscure the meaning of the message anyway in ham radio terms, but these tags aren't capable of that, so it's no big deal. There's also no limits on antenna gain. In the ISM band, if you're using it as an ISM band, you're limited to 6 dBi of antenna gain. Well, as a ham band, there's no such limits. These antennas have 13 dBi of gain. You could quite easily get antennas with significantly more than that. So the commercial Gen 2 reader, I have one here. This thing. So this is a Symbol XR400. This was $250 on eBay. As I mentioned, it's compliant with the ISM rules, so it's very rapidly frequency hops, about 100 times a second. Now what that means is if we're trying to port that to a ham radio application, the one thing that we can't do with that is figure out what frequency it's on and then identify the transmitting station. That's one of the big key things that you have to do as a ham radio operator. You have to identify your station. And if we're frequency hopping 100 times a second, that's virtually impossible. You could theoretically do it with a very, very fast spectrum analyzer and some very clever software, but it's really quite prohibitively difficult. This reader, because it's ISM, it's limited to 1 watt of output power. It's limited to 6 dBi of antenna gain, and it actually checks for a correct antenna. If you just try and connect this thing to any old antenna, it'll just turn off the read port. You can see there's 8 RF sockets on here. That's actually 4 receive ports and 4 transmit ports. So I can connect 4 pairs of antennas to this. And if they're legitimate antennas, it'll turn the port on and start dumping power out of them. If it doesn't detect a legitimate antenna, it'll just disable the port. So how can we improve on this? How can we make this reader better? Well, the first thing to do is obviously replace the antennas. It's really easy to get hold of high gain Yagis. These were about $50 each. So we've got 13 dBi gain compared to the 6 dBi gain of the reference antenna. So overall, we've got 7 decibels of improvement in the antenna system. Now, if we go back to the radar range equation, we should see a range increase that corresponds to the square root of the antenna increase. So because we're working in decibels, we can actually take a square root by halving. So if we've got 7 dBi improvement in the antennas, we should expect to see 3.5 decibels of improvement in read range. As it works out, 3.5 decibels is a factor of 2.25. And if we compare that to our reference of 30-foot read range, which is what this reader does out of the box, we would expect to see that these antennas should give us a read range of about 67.5 feet, assuming that the radar range equation is correct. First, though, we need to defeat the antenna protections. We need to find a way to get this reader to talk to these antennas. It's actually really easy to do. The way that they've protected it is they put a 10 kilo ohm resistor between the active element of the antenna and ground. And then they check the DC impedance of the antenna. If it's just a normal antenna, there's going to be one of two DC impedances. Either it's just a piece of wire sticking up in the air, that's an antenna, in which case that has infinite impedance. It's open circuit at DC. Alternatively, if you've got an antenna like this, you can see these active elements right here. This is a loop. So at DC, this is zero impedance. So how do we match the zero impedance of our Yagi, or zero DC impedance of our Yagi, to the reader's expected 10K? Well, it's actually really easy to do. You start off by soldering a 10K resistor inside the antenna port, inside the reader between the read port and ground, so it sees that DC impedance. And then the next part is to convert the zero impedance of these things at DC to open circuit effectively. And that's where one of these things comes in. This is just an ISM band filter. So all this does is whatever you put into it, it filters out anything that's not within the 902 to 928 megahertz ISM band, and that comes out. Fortunately, the input of this is a capacitor, meaning that at DC, it's open circuit. So if we stick one of these filters between the transmitter and the antenna, we've then got the 10K impedance inside the transmitter, we've got effectively open circuit at DC from the antennas, and we're all good. So we did this, and we tested it, and we got a read range of 70 feet. So consistent with the radar range equation, and good first confirmation of the theory. So the next stage is power amplification. That's the other big switch, the other big lever that we can throw to improve our read range here. We could just put an amplifier on the output of this. I mean, we can use the same techniques to defeat the antenna locks to make it think that it's talking to its own antenna when it's actually talking to a big beefy power amplifier. That's perfectly viable. The problem with it is that we're not compliant with ham radio rules. We need to identify the station. Secondly, another problem with it is that because it hops frequency so rapidly, it's virtually impossible to see that signal on a spectrum analyzer. So it's very difficult to measure it, it's very difficult to quantify it, and it just makes designing an RF chain that much harder. So overall, yeah, we could quite happily amplify the signal from the reader, but it's kind of inelegant, and it's probably a pretty serious violation of FCC rules because you're not identifying the station, even though you're operating under ham radio rules. So a better Gen 2 reader, the link here is a reader for this little black box here. This is, I don't know if you can all see this. This is a USRP, the Universal Software Radio Peripheral. This is a software radio device. So effectively, the computer does all the work of modulation and the coding and figuring out how to actually put those bits on the radio. And then the USRP just takes that data stream over USB, upscales it to whatever baseband frequency you've got. It's open source, and the big advantage that it gives us is frequency control. It sits on a specific frequency, just one frequency that's set in software, and we can control that. So instead of having to follow this frequency hopping system, we now have one frequency that we need to worry about. This package also includes a Gen 2 sniffer. It does need the USRP2, but if you run this thing, you can actually sniff the kill and lock codes from any reader that you like. It doesn't include the ability to read the responses from the tag, just because those signals are so very much smaller. But certainly you can sniff the kill code and the lock code as they're sent by the reader. Another little tweak that I've made to the USRP, I've actually upgraded the clock in it. I do a lot of work with GSM, and GSM requires a 52 megahertz clock, whereas the stock USRP and this RFID system needs the standard 64 megahertz clock. So switching between those two, I don't know how many people use USRPs and are interested in things like GSM. There's an open source hardware project called the Clock Tamer. Extremely accurate clocking, very programmable, very controllable. I highly recommend it to anyone who's doing work with the USRP. So how do we identify the station? Now that we've got a fixed frequency, how do we identify? Well, all we have to do to identify the station in compliance with ham radio rules is transmit a call sign. We have to transmit a Morse code call sign just with an unmodulated carrier. So not tremendously difficult to do. We just need to find a way to generate that carrier. Now, obviously we're working with the USRP, so obviously we could use that to transmit our radio signal if we wanted, but to be honest, I couldn't be bothered. There was an easier way to do it. That easier way would be a second transmitter. If you have a second transmitter on the same frequency, slightly higher power, and that second transmitter sends out your call sign, then any receivers that are tuned to that frequency, they'll hear the RFID signal, and then when that second transmitter kicks in, it'll overwrite the RFID signal, and you'll hear the call sign on top of it. So it'll effectively DOS the system for a second while it identifies, but it's just for a few seconds every 10 minutes or so, so it's not really a major deal. So we need an easily scriptable 900 megahertz transmitter. The easiest transmitter that I was able to find was one of these. This is the IMME. This is rapidly becoming a hardware hacker's favorite device. They don't normally come with SMA connectors and JTAG on the bottom. That's an aftermarket modification. But Travis Goodspeed did a lot of work with these things because there's no firmware security. So if you go to Travis's blog, there's a tutorial for how to wire a JTAG connector into it. There's source code for a new operating system. And as long as you've got a good FET to program the thing, you can just write your own operating system for it. Quite a powerful little device, little LCD screen, keypad, very, very wide frequency range, and about 10 dBm of output power. So pretty flexible, pretty powerful, and all we really need to do is connect that to the USRP, mux those signals together, having matched the power levels together first. Because if we look at the signal from the IMME, that's coming out at about 10 dBm, 10 milliwatts. The signal from the USRP is at about 500 milliwatts. So we need to match those levels. And the way that I do that is by somewhat attenuating the signal from the USRP, somewhat amplifying the signal from the IMME, and then just mixing them together with a standard power splitter. So it's not tremendously difficult to do. A quick demo of the station identification. Let me just turn on my power chain here. So this is just a ham radio receiver. It does actually transmit as well, but at the moment I've got it receiving 915 megahertz. So I'm right in the middle of that ISM band. And if I turn the volume up here, so that clicking noise, that's the signal from the reader. That's the RFID interrogator pulses coming out, telling the tags to wake up and start doing stuff. And if I push a button on the IMME, you can hear how many people copied that. Nobody copied that. Did you actually hear the signal? Okay, let me do that again. So that's the RFID. So we've taken care of identification. So it's really easy to do. Just match the frequencies together, mix the signals, match the power levels, and we're in business. So we've now got a fully compliant ham radio transmitter. We're identifying the station. We're operating with complete compliance with ham radio regulations. We're now good to go with up to 1,500 watts of power. That's rather a lot. At UHF, you're talking about line of sight communication. You don't get